Okay, so picking up where we left off in the first video for section 2.2, we defined what a subset was. And one thing I emphasized in that video was that every set is a subset of itself. And again, that may seem a little bit counterintuitive because intuitively speaking, when we use the term subset in regular language, we tend to think of something that's smaller than the set that it belongs to. But the mathematical definition of subset allows for a set to be a subset of itself. However, oftentimes we do want to talk about that more intuitive idea of what a subset is. So if we specifically want to talk about A being a subset of B, but in such a way that the two sets are not equal, so in a sense A is actually, smaller than B, we call that a proper subset. And we can write it using this notation here. Notice this is the same symbol that we use for subset, but without the line under it. You can compare these two symbols for subset, that subset relation, as, a less than symbol, or a less than or equal to symbol, which also has a line under it. It's a very similar concept. Okay, basically when we say that A is a proper subset of B, what we're saying is that every element of A belongs to B, but in addition to that, B has more stuff in it than A does, so that they can't be equal. B is, in a sense, larger than A. Okay, now, we showed in the previous video also how to determine whether one set is a subset of the other using some examples. And that was using the definition directly. If we want to show that A is a subset of B, then every element that belongs to A, we want to show that it also belongs to B somehow. But there's a less direct way to approach that. And you wouldn't necessarily think to do this in most applications, but it turns out to be really useful. And that's by doing what's called a proof by contradiction. This is something that we explore in greater detail when we get to the next unit, which is on formal mathematical logic, kind of the idea of what a proof by contradiction is. But in math specifically, proofs by contradiction are incredibly, incredibly powerful and very, very useful in a ton of different contexts. Where we're going to use it here is to show that the empty set is a subset of every set. And that, again, may seem counterintuitive, but let's get through this kind of little blurb here before we jump to that. So a less direct way of showing that A is a subset of B is to assume the opposite, or the more correct term there is negation. And again, we'll define that in the logic chapter. We assume the opposite of what it is we want to show. If I want to show that A is a subset of B, I'm going to assume that A is not a subset of B. And then what I want to show is that this must have been wrong somehow, that this initial assumption could not possibly be correct, and so the only other alternative is A is a subset of B, the thing I wanted to show. The way that we do that is we make this assumption and then show that this logically leads to a contradiction somehow. That contradiction gives us the result we're looking for. So how do we do this when comparing the empty set? Well, my goal here in this paragraph is to show that given any set A, it doesn't matter what A is, literally any set at all within any universe, I want to show that the empty set has to be a subset of this. So using this indirect approach, let's assume that that's false. Let's assume that the empty set is not a subset of A. What does that mean? Well, remember, if the empty set was a subset of A, that would mean that every element of the empty set belongs to A. The opposite of that is to say that the empty set contains an element that's not contained in A. That would mean that this is not a subset of this. So to say this symbolically literally means the same thing as saying that the empty set contains an element that's not contained in A. But that right away is a contradiction, because the empty set, by definition, doesn't contain elements at all. So to say that it must contain something not contained in A is inherently false. That contradiction implies that this initial assumption here had to have been incorrect. It is incorrect to say that the empty set is not a subset of A. Therefore, the opposite must be true. The empty set is a subset of A. And because A was chosen arbitrarily, this proves that the empty set is a subset of everything. Okay? That's counterintuitive because it feels like a set that contains nothing shouldn't be contained within some other set that contains something. But in a mathematical context, in the sense of the definitions that we use for these things, it's 100% true. Okay? Now, let's do an example that's going to lead to kind of a formula that we'll close this section out with. I want to list all of the subsets of this set here, A, B, C. Okay? And I'm going to do this, and I'm going to try to do this in a structured way. So I don't want to just randomly think of subsets. I want to do this in a way that's organized and lets me know that I've thought of everything that I needed to think of. So first of all, we know immediately from this previous paragraph that the empty set is automatically a subset of this because the empty set is a subset of everything. So that's easy enough. Now, this is the set containing 0 elements. Let me see if I can determine all subsets of this set here that contain exactly 1 element. So that would be the set containing A, the set containing B, and the set containing C. Those are the only elements that I had to choose from here. So that would imply that the only sets that can contain 1 element, or sorry, the only subsets of this containing exactly 1 element are these 3 right here. Okay? What about the sets, or what about all of the subsets that contain exactly 2 elements instead of exactly 1? Well, there's A, B, and then there's A, C. And before I finish this list, notice that this accounts for all of the sets containing exactly 2 elements that would have A in it. Because remember, I've written A, B here. I'm not going to create another set B, A. Reversing the order of these 2 elements doesn't make a new set. So it's pointless to write B, A if I already have A, B. But A has no other elements that it can be paired with, and so the only other set that makes sense here is the set BC. You should be able to see that those are all of the subsets that would contain exactly 2 elements. Okay? Well, how many sets can we list that contain exactly 3 elements? Well, remember, the original set only had 3 elements to begin with, so that is the only subset that would contain all 3 of them. There's no other way to create a set containing exactly 3 elements from this. Okay? So notice kind of the way that we approached that. I didn't want to just randomly write sets. I wanted some sort of structured, organized approach so that I could be sure that my list is complete. Now, what we're going to be doing with this idea is not, continually listing out a bunch of subsets, but rather trying to determine the total number of subsets that a particular set can have. And it turns out that you don't need to do this listing approach to determine that. Notice if instead of I was talking, well, let me back up. How many subsets did we end up with? There's 1 here, 3 here, 3 here, and 1 more here. That totals to 8. This set of 3 elements contained 8 subsets. Okay. Now notice there was nothing special about the elements A, B, and C. If I replaced this with the set 1, 2, 3, I still would have ended up with 8 extremely similar looking subsets. It's just the symbols would look different, but the number of subsets would be identical. And in fact, any set containing 3 elements in it will have exactly 8 subsets because the symbols are not what matter. It's the number of elements that matters. Is there a way of not only determining that fact, but also determining the number of sets, or the total number of subsets that a set containing n elements, or just some arbitrary number of elements, is there a way of determining how many subsets a set will have without having to list them? And the answer is yes. In order to determine that, we're going to redo that example up here without listing the sets, but taking a different perspective. We're going to create a tree diagram, okay? And the tree diagram is going to start it's going to be asking a question regarding each element. So I'm going to say, is A in the subset? Okay? Now, thinking about this, this is a question that we're asking of any one of these subsets. Notice that A belongs to some of them, here, here, and here, and here, but it does not belong to others. So if I were, instead of listing all of the subsets out, if I were saying, let's consider some arbitrary subset of ABC, I can ask this question. Depending on which subset I'm thinking of, the answer is either true or it's false. And so we consider those as two branches on a tree. True, false. Oops. Regardless of, let me make that a little bit longer. Regardless of the answer to that question, or sorry, regardless of which subset we're talking about, we have to have one of these branches being the correct answer. Now, what if I move on and say, considering that same subset, whatever it is we're thinking about, is B in the subset? Well, we've made it here or here based on the previous question. So I have to ask this question in each of those possible scenarios. Okay, and I didn't actually leave myself enough space here. I should have thought that through a little better. Let me do this. I'm going to make this branch kind of go this way to leave myself a little bit more space. Okay. So if A is in the subset, then B is either in the subset or it is not. We've dealt with A, now we're dealing with B. True or false. Okay? And that leads now to 4 possible scenarios. For any subset that I'm talking about, A might be in the subset and B might be in the subset. A might be in the subset and B may not be in there. A may not be in there and B may be in there. And A and B may both be absent from the set. So this considers 4 possible scenarios once we've asked the question about A and B. Finally, I have to make these longer. My tree is not looking very good because I wasn't really being careful about the amount of space that I needed here. Your book creates the same tree and does a much better job graphically than I'm doing, so pardon my sloppiness here. Let's ask the question if C is in the subset. Remember, that's the last element that we could consider. Okay, so now we're in 4 possible scenarios. Each of these branches off into 2 possibilities. Is C in the subset? Well, it either is true or it's not, false. It either is here or it's not. It either is here or it's not. It either is here or it's not. This considers all possible cases. Now, if I start here at the beginning of my tree and follow any one of these paths to one of these endpoints here, that is going to correspond to one of the sets that I listed out in the previous example. So for example, let's follow this path. If I say, is A in the subset? True. Is B in the subset? False, which takes me here. Is C in the subset? True. Then I'm looking at the set that contains A and C, but does not contain B. That's this subset right here, AC. So this path on our tree is a visual representation of this subset, right? Oh, I realize I'm pointing at it without pointing at it. that tree, that branch of the tree is corresponding to this subset right here. And so this set of all possible paths from this point to these points is going to be, or the number of different paths, I should say, from this point to any of these points is going to be the same as the number of subsets of my set ABC. Okay? Now, how many endpoints did I have here? Well, I have 8. Not surprising because that's the number of subsets that we were dealing with. But is there a way to do something similar to this with larger sets than just 3 elements? Yes, but drawing the tree becomes very, very cumbersome. And I don't want to have to do that. I want to be able to come up with an answer much more quickly. The way that we do that is to notice right here at the beginning, there's only one choice to be made, this starting point. Once I get here, this branches off into 2 directions. Now we have 2 dots here, 2 choices which is, A belongs to the subset or it does not. But those two choices each branch off into two more choices, leading to two more points on this tree. So that would correspond to 2 times 2, or 2 squared. Different endpoints here. 2 squared is 4, and you can see all 4 of them. 1, 2, 3, 4. Each of those 4 paths will branch off into 2 separate paths, so that doubles the number of choices once I get to this part of the tree. 2 cubed. Notice also, the number 1 here is equivalent to 2 to the 0 power. You should know this from algebra. Any non-zero number to the power of 0 is equal to 1. And 2 is the same thing as 2 to the first power. This indicates that the number of subsets contained in any given set is a power of 2. 2 to the third power is equal to 8. That was the answer to our previous question. And this generalizes, as you can see from this tree diagram. So to give us a more general formula to work with, if A is a set containing n elements, then A has a total of 2 to the nth power subsets, okay? And we can now use that to answer this question for much larger sets without having to list things, without having to create these big complicated tree diagrams. Before we do an example, notice that A is, as we said before, a subset of itself. And if we aren't interested in considering A amongst our list of subsets, in other words, if we only want to know the total number of proper subsets that a set contains, then all we need to do in this example, for example, we would just remove that one set that's equal to A, or that's equal to the set that we started with. So that would just take the total number of subsets and subtract 1 from it. In other words, if A is a set with n elements, then A is going to have a total of 2 to the n minus 1 proper subsets. That minus 1 indicating the set A that we're removing from our list. Okay? So one example, and then we can wrap this up. Let A be the set of all positive odd numbers less than 10, and determine the total number of subsets and proper subsets of A. So this is just a description in words. We need to know how many elements are in this set in order to use that formula. So I'm going to list them, changing the way that we represent this set. The set of all positive odd numbers less than 10 are the numbers 1, 3, 5, 7, and 9. This is our set A. How many elements are in the set A? Well, remember we use this notation. N of A, number of elements in A, is 5. You just count them, there's 5. Okay? Now, how do we determine the total number of subsets of A? Well, the formula that we just derived said that if there's 5 elements in A, then the number of subsets of A is 2 to the power of 5. This is equal to 32. Notice I don't need to list them all out. That would be a lot of sets to list out. I don't need to create this increasingly complicated tree diagram to find all 32. I can just use this formula directly. It's much, much more efficient. What about the number of proper subsets? Number of proper subsets of A. Well, that formula was similar. It's still 2 to the 5th power, but then we subtract that one subset that consists of all the elements in A. That would be 32 minus 1, or 31. So here's our 2 answers to that question, and that's going to wrap up section 2.2.